What's up, my people? Last week we talked about Q, heat, and how to relate Q to delta H, which is the enthalpy. So Q is the heat, right? It's the heat released or absorbed by some process, and delta H is the heat per mole. Okay. So last week we talked about delta H is equal to Q divided by however many moles of the substance are involved in that process. So today we're going to talk a little bit about Q and how to find Q. So first, before we do that, we want to talk about specific heat. What specific heat is the quantity of energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. Okay, and the specific heat of water is 4.18 joules per gram degrees Celsius. Okay, or sometimes it's written as joules per gram Kelvin. Most of the time, I'll give you the temperature in degrees Celsius here because that's what our thermometers will measure. So, the formula to find Q is equal to mc delta T. Now, C is the specific heat, M is the mass, and delta T is the change of temperature. Okay, so what we're going to be dealing with is a process that involves a change in temperature, because if heat is added, there's going to be a positive change in temperature. If heat is taken away, there's going to be a negative change in temperature, right? So if heat is released, there's going to be a negative change in temperature. If heat is added, there's going to be a positive change in temperature, right? Um, so here are the units we're going to be using. So in heat is joules, mass is grams, and temperature we're going to use degrees Celsius for the most part. So that leaves C to be joules per gram degree Celsius. So an unknown example number one, an unknown substance with a mass of 50 grams is heated from 298 kelvins to 373 kelvins. While heating, the substance absorbs 750 joules of energy, what is a specific heat of the unknown substance. So this is an easy one. The mass is equal to 50 grams. The Q is equal to 750 joules. Ti and Tf. Okay, Ti is equal to 298 kelvins. Tf is equal to 373 kelvins. And so delta T, delta, the change is always final minus initial, Tf minus Ti. Okay, delta T is equal to 373 minus 298, which of course is 75 kelvins. Okay, the formula is Q is equal to mc delta T, and C is going to equal Q divided by m delta T. So then C is going to equal 750 joules divided by 50 grams times 75 kelvins. Okay, so that's going to be C is equal to 0.2 joules per gram Kelvin. Okay, so the next thing I am going to ask you guys to do these two problems, and then I want to move ahead to talk about calorimetry for a second. So calorimetry is the measurement of heat that is transferred in some sort of reaction or a physical process. So there's sort of two types of calorimetry that you'll see. Or there's a couple types of calorimetry. So you'll see, um, like in this first question, that this would be called a bomb calorimeter. So you'd have water in here, and you'd have some sort of fire. That's fire right there. And some sort of reaction taking place to heat up the water. And we're going to figure out how much heat got released by this reaction here and went into the water. So you can figure out the enthalpy based on this. Okay. So that's one type of calorimetry. Okay. And then another type of calorimetry would be if I had some sort of metal. Okay. And that's going to happen in this one. Okay. So you might have some sort of metal, like aluminum in this case, and then you have uh, your water, and you put the aluminum metal into the water, and um, and that's going to heat up the water. So you can figure out based on um, the heat that the water gained, you can figure out how much heat the aluminum lost. Okay. And then a third type that we're going to see is over here. This is enthalpy of solution. So in this case, we're going to have some sort of salt, lithium bromide, and that goes into water. And it dissolves in the water and causes the water to change temperature. So let's go back to this first one. This is the bomb calorimeter. A calorimeter contains 1,000 grams of water. When 2.8 grams of gasoline is combusted, it changes the temperature of the water from the calorimeter from 298 to 330 kelvins. How much heat does this chemical process release? Okay, so it's important for you to know that how much heat the water gains is equal to the opposite of the heat that that the process releases, and how much if the water loses heat, that's equal to the amount of heat that the process itself gained. Okay, so in this case, we have 1,000 grams of water. So that is the mass of the water. Mass of the water is 1,000 grams. We have the mass of the gasoline is equal to 2.8 grams. Okay. We want to find, so we have the initial temperature of the water is 298 kelvins. The final temperature of the water is 330 kelvins. Okay. We know that the specific heat of water, this is something you want to memorize, is 4.18 joules per gram Kelvin or gram degree Celsius. Okay. Each individual Kelvin is the same as each individual degree Celsius. So if you say gram degree Celsius, it's the same as saying gram Kelvin. It just depends on what the temperature is in. Okay. So then you have, so you're going to say, okay, the Q water is equal to the negative Q of the gasoline. Okay? So the heat that the water gains is equal to the negative of the heat that the gasoline loses. Okay? So then based on this, we can figure out how much heat the gasoline loses. Okay? So we can just say, we know that the Q of water is just going to be MC delta T of the water. Okay? So we can say QW is equal to MC delta T. QW is equal to 1,000 grams times 4.18 joules times, in this case, delta T is equal to TF minus TI. So delta T is equal to 32 kelvins. So 1,000 times 4.18 times 32. And this is joules per gram Kelvin. So Q water is equal to 1,000 times 4.18 times 32, which of course is 133,760 joules. Okay, so oftentimes when it's this big, we'll say Q water is equal to 133.76 kilojoules. And then we'll say the Q of the gasoline is equal to the negative Q of the water. So that's negative 133.76 kilojoules. Okay, oops. So kilojoules. So that's how we find the amount of heat that the gasoline loses. Now, in this one, we're going from, so in this one, we're going to try and find the specific heat of aluminum. It says a 28.4 gram sample of aluminum is heated to 39.4 degrees Celsius, then is placed in a calorimeter containing 50 grams of water. Temperature of water increases from 21 degrees Celsius to 23 degrees Celsius. What's the specific heat of aluminum? Okay, so in this case, we want to separate this. Like, we want to talk about aluminum and we want to talk about water. Okay, so the mass of aluminum is equal to 28.4 grams. Okay, the initial temperature of the aluminum is 39.4 degrees Celsius. Okay, and then it says the final temperature here, okay, is 23 degrees Celsius. TF is equal to 23 degrees Celsius. And then we can talk about the water. The mass of the water is 50 grams. Okay. The specific heat of water is equal to 4.18 joules per gram. See, this time we're dealing with degrees Celsius, so we're going to say degrees Celsius. And then TI, the initial temperature of the water, is 21 degrees Celsius. And the final temperature of the water is 23 degrees Celsius. Okay, so it's important for you to know that the heat gained by the water is equal to the negative of the heat lost by the aluminum. Okay, so if we know that Q is equal to MC delta T, so we can say that Q, no, I didn't want to do that. So then I can say MC delta T for water is equal to MC delta T for aluminum. Negative, okay? So MC delta T, this is just the expression for Q, okay? So MC delta T is the equation for Q. So if I say Q water, I can also say MC delta T water, okay? So then I'm going to plug this in and I'm going to say, okay, we know that the mass of the water is 50 grams. So 50 grams times the C of water is 4.18, specific heat of water, 4.18 grams degrees Celsius times, okay, delta T here, 23 minus 21 is 2 degrees Celsius. So that's 2 degrees Celsius. And then is equal to the mass of aluminum is 28.4 degrees Celsius. Okay. In this case, delta T is equal to 16.4 degrees Celsius, right? So, and it's TF minus TI. So this is negative 16.4 degrees Celsius. So what we want to find is CW, right? And then this is negative 16.4 degrees Celsius. Okay, so then what we're going to do, we are going to say 50 grams times 4.18 joules per gram degrees Celsius times 2 degrees Celsius divided by what's over here. So I messed up. Hold on. This should say 28.4 grams. I'm so sorry. 28.4 grams times negative 16.4 degrees Celsius is equal to CW, C aluminum. Okay, so this is all negative. So these two negatives are going to cancel out. We have a negative here and a negative here. They're going to cancel out. Okay, so we'll make those both positive. We get the specific heat of aluminum is equal to 50, boom, times 4.18 times 2 divided by 28.4 times 16.4. Boom. Enter. We get the specific heat of aluminum is 0.897 joules per gram degrees Celsius. Ooh. Okay, so I happen to know that that is the specific heat of aluminum. No big deal. I know that. So that's the correct answer. Boom. So the last type is molar enthalpy of solution problem, and these are the most involved ones. Okay, so when salt dissolves in water, when salts dissolve, there are 3 steps. Number 1, energy is required to break the ionic bond. So in this case, LiBr would go to Li plus and Br minus. Okay. Number 2, attractions between water molecules are broken to make space for ions to fit. Okay? And so these first two steps, both of these first two steps, are endothermic. Okay, and then the third step is exothermic. Okay, and that's where the ions form attractions with water molecules. Okay, so in this third step, the Li is going to be attracted to the negative part of the water, and the Br is going to be attracted to the positive part of the water. So remember, so this part is exothermic because there is an attraction being formed. In these first two steps, attractions or bonds are being broken. All right, so so we can find out how much heat is released or absorbed when 1 mole of LiBr dissolves. Okay, so it says in an experiment, a student added 1.01 grams of lithium bromide to 12.21 milliliters of water at 20.1 degrees Celsius. After stirring, the temperature of the mixture rose to 31.3 degrees Celsius. Calculate the molar heat of solution for lithium bromide. So, what you can do here in the in the in the problem with the aluminum and the water, the aluminum and the water are two separate things. When you have when you're talking about a solution, you're talking about all of it together. Okay. So what you can say here is that the heat lost by the salt is equal to the heat gained, but the opposite of the heat gained by the solution. Okay, so what we're going to find is this. Boom, we're going to find the heat gained by the solution. All right, so the mass of the solution is going to equal the mass of the water plus the mass of the salt. So that's, in this case, so 12.21 milliliters of water is the same as 12.21 grams of water. So 12.21 grams plus 1.01 grams is 13.22 grams. Okay, and then the specific heat, for even though it's a solution, you can still use the specific heat of water. It's close enough to the specific heat of water. So we're going to say C is equal to 4.18 joules per gram degree Celsius. Okay, and then we're going to find delta T is equal to TF minus TI, and that in this case is 30.3 degrees Celsius minus 20.1 degrees Celsius. Okay, so I'm going to need this space in a second. So I'm going to find Q solution is equal to MC delta T, which is equal to 13.22 grams times 4.18 joules per gram degree Celsius times 11.2 degrees Celsius. And so that's going to give you 13.22 times 4.18 times 11.2 is equal to 618.9 joules. Okay? So now what you need to know is that the heat lost by the salt is equal to the negative heat gained by the solution. So heat lost by the salt is equal to negative 618.9 joules. We know that it's an exothermic process because when the salt dissolved, it rose the temperature of the water or the solution. So then what we can do is to find the molar heat of solution, that would be delta H in this case, is equal to Q divided by moles reacted. And so what we have to do is we have to find the moles here of LIBR that dissolved. Okay, so we have 1.01 grams, and we're just going to divide by the molar mass, 1 mole divided by what is it, 86.84. 86.84 grams, and that's 0.0163 gram. And then we get delta H. Sorry, this is moles. Then we get delta H equal to negative 618 joules divided by 0.01163 moles. We get delta H is equal to 49,183 joules per mole, or negative 49.2 kilojoules per mole. Okay, that's it. Sorry, I was whispering. My ears waking up.